So I guess we can start. Good morning again, everybody, and welcome to the first plenary lecture of the 8th ECM. It's a great pleasure to introduce Alfio Quarteroni from Politecnico di Milano in Italy and EPFL in Lausanne, Switzerland. Alfio is a professor of numerical analysis and the director of MOX at Politecnico di Milan. I will not read his whole citation here because it would be too long, but just let me mention that he is a co-founder and president of MOX-Off, a spin-off company at Politecnico di Milan, where math is brought into industry and applications. And he received many prizes, in particular the NASA Group Achievement Award for pioneering work in computational fluid dynamics, and the Premio Capodolando Prize, the Ghisleri Prize, and the Galilei Prize for Sciences in 2015. So let me leave it with that. I could go on forever. He's a SIAM Fellow and a member of Academia Europaea and the European Academy of Science and the IMU Circle. His research interests are in numerical analysis and scientific computing, and he has carried out a lot of work for the Swiss long-range experimental solar-powered aircraft project, and also for the optimization of the Alinghi yacht, the winner of the America's Cup. So without further ado, I would like to ask Alfio to start his talk. Thank you very much.
Thank you very much, Mr. President, and it's an honor to be introduced by you. And I'd like to thank the scientific committee and the organizing committee of this beautiful event for inviting me. It's a great honor to be here this morning. So as you see, the title of my talk is The Bit of Math. And as you can guess from the picture, I will be talking about the way we can mathematically modeling the heart. This is made of different steps. The very first one, which is perhaps the most challenging, is how to build a mathematical model for the heart. And the second one is how to solve the equations, which are differential equations, partial differential equations, ordinary differential equations that are involved in this model. And then how to develop then algorithms that are efficient and accurate to get a numerical solution. And last but not least, how to face clinical applications. And here we have multiple purposes. The first one is to help for getting a better understanding of the physiology of very complicated processes like those that occur in our heart. The second one is hopefully to help doctors to improve the care treatment and also to design more efficient surgical interventions. So it's a very ambitious project, and I will start from the mathematical ground of this project. And first of all, let me give you, really in a nutshell, a few, say, notions about the heart physiology. As we all know, heart is one of the most important organs that we have in our body. It's there to ensure that we have blood supplied to all our organs and all our cells. It's a 4-chamber organ. We have 2 atria and 2 ventricles. These are cavities, actually. So the blood enters our heart from the venous vessel, which is called the vena cava. It enters into the what is called the right part of the heart, the right atrium. Then it passes through this valve. It enters the lower part, which is the right ventricle, and then through this pulmonary valve, it goes directly to the lungs, where it gets oxygenated. So it releases CO2 and other toxic substances, and it intake oxygen from their respiration. And then it brings this new blood, which is this oxygenated blood, back to the heart through 4 vessels, which are called the pulmonary veins. And this new blood enters the left atrium in the upper part here, and then through this valve, which is called the mitral valve, it goes into the left ventricle, which is supposed to be the most important chamber of the heart. And when this squeezes, when this compresses, this blood will be ejected through this valve, which is the aortic valve, into the main aorta, and through the aorta it will reach all the rest of the body. So this is somehow the mechanical function of the heart. The heart is a mechanical pump, but what does make this pump functioning? What is the engine that is behind the whole story? Well, the engine is electricity. And actually, at every instant of our life, there is an electrical impulse that is generated in this point, which is called the sinusoidal node, is a bunch of cells that say spontaneously are activated and act as a pacemaker, say, natural pacemaker. So there is an electrical field that is created. It propagates through the two atria, and then through this set of high-speed fibers, which are called Purkinje fibers, it reaches the lower part of the heart, the ventricles, and every single cell is then electrically activated. And this is very important because then at that level, every single cell, there is a very complex mechanism that creates a force, an active force. It's called the active force that makes this filament, say, sliding, and in particular, relaxing and stretching. And the overall action of these microscopical forces determines what is known as heart deformation, compression and dilation and relaxation. And this is what makes possible the ejection and intake of blood into the organ. So this is a very complex mechanism, say, which is very short to describe at the physical level. But how can we proceed mathematically? We like to be able to describe the whole mechanism through equations. And for that, we split the whole physiology into different components that we call the core cardiac mathematical models. And the first one is there to reproduce the electrophysiology, so the creation of the electrical field. The second one, the active mechanics, namely the force that is generated at every single cardiomyofilament. The third one is the so-called passive mechanics, that is the physical process that enables heart to compress and to relax. And then we have fluid in the chambers because we have blood. So we have the four core model, which has to see with the fluid dynamics. And then we have the valves. We have four valves that open and close very suddenly. So we need models to describe the valve's motion. And finally, we have what is called the myocardium perfusion. So heart is made of the myocardium, is a muscle. And the muscle itself, so the heart itself, needs to be nurtured by blood. And this is made possible by the presence of the coronaries. So the coronaries receive blood from the heart, from the aorta, say, and then bring this blood to the myocardium. So those are the 6 basic core cardiac models. And I would like to tell you a bit more about that, just in terms of mathematics. I will not derive, of course, all these models because this will take for a very long time. But let me give you a flavor about the mathematics which is behind these core cardiac models. Sorry. So the very first one is what is called cardiac electrophysiology. And this is the process of generating an electrical field, which is expressed here by this equation, which is called the monodomain equation. We have more sophisticated equations that we can also use that are called bidomain equations, but in essence that they share the same mathematical structure. So let me just focus on this for simplicity. So as you see, this is a partial differential equations, which is time dependent. And we have a diffusion component here. We have a reaction component, and then you have an extra a forcing term, say. So this is, in mathematical terms, a time-dependent reaction diffusion, nonlinear reaction diffusion, partial differential equation. The unknown is U, and U is the transmembrane potential. What does that mean? Well, if you just look at a single cell, we have opening and closing of these channels. And through these channels, these ions of calcium, potassium, and sodium go back and forth. So they migrate, they transit through these channels. And this create a polarization and the depolarization that is expressed by this curve here. This takes place over a heartbeat, which typically is a little less than 1 second, right? You start from the rest, you have a short repolarization. This is called the action potential, is expressed in millivolt. We go from, say, from the ventricle from -8 or -90 up to +60, say. You have a peak here, spike. Then you have a short repolarization, a plateau, which is followed from the resting. Okay. So you create a transmembrane potential. This is expressed by U. And U is the difference of potential between the external part and the internal part of the cell. And this satisfies this equation. Now, the reaction term depends on this variable that is called the gating variables. And those are provided by solving a system of ordinary differential equations that take place at every cell level, at the cell level, at every single cell, say. And the quantities that are represented here are, say, the concentration of these ions. And the so-called gating variables, which are binary variables, they are equal to 0 if this channel is closed, or 1 if this channel is open. So this is a coupled system of PDEs and ODEs. The external force here is the, say, spontaneous electrical stimuli that is generated at the sinusoidal node that can be, of course, modeled. Of course, we have many different models for the ionic activity, and here I name some of them, those that are more frequently used, and these reflect into a different type of model for, say, the ionic species. So that's the very first model, the one that, say, regulate the propagation of the electrical field. And here you see the numerical solution of this model. You see one heart on the right-hand side. You see the cross-section, sorry, the longitudinal section of this heart. When it's blue, it means that it is at rest. Otherwise, you have a stimuli that is generated in the sinusoidal node. It propagates, this electrical field, it propagates to the atria and then to the ventricles. And you have a color map here. And this color map provides you for every single point of this heart the value of the transmembrane potential. You see the same simulation on the left-hand side, but you see it from the external surface, it's called pericardium. Sorry, the epicardium, the external membrane of the heart. So this is already the result of a numerical simulation that you obtain after numerically approximating the previous system of partial differential equations. This is a different view. What you see here are the isolines of the activation time. So you see every line here connects points that are electrically activated at the same time. That's very important for the doctors because when you have such a map, this tells you that this heart is behaving correctly in terms of rhythm, in terms of rapid rhythm. But when this map is very perturbed, then this is a clear symptom that the heart is not working properly. And we'll see examples later on. So please note that this is not invasive. It's something that mathematics allow us to do to create this realistic electrical propagation on the surface of the heart and then provide the doctors with very important tools. Like the one that you see here, this is a ventricle of a real patient which suffered from very, say, severe arrhythmia. And this is due to the fact that there are some biomarkers, as you see here on the right-hand side. The biomarkers are those that characterize the specific misbehavior of the electrical field. You have slow zones of conduction, or you have lines of block through which the electrical signal cannot pass. And this is due to, say, fibrotic, for instance, tissue, which might be there because of a previous heart attack, say. And the point here is that doctors would like to understand which are the biomarkers and then identify points for the ablation. And they did enter through a catheter and the camera with a laser point, and they go and burn literally the tissue on very selected points in order to say restore, hopefully, this correct circulation of the electrical field. This is very experimental. There's very little theory, and it's very invasive. It takes several hours for patients. So what we try to do here to help them is to compute for the same ventricle for that specific patient the electrical propagation, and identify through this numerical simulation those biomarkers before the doctor can operate. Now, this was the electrical action, but then the electrical action is there to allow the heart to contract and to relax. And this is possible because at the cell level, so this is a kind of microscopic model, at every single cell, you have a deformation S, a sliding that is generated because you see the sarcomeres, which are the basic units of the heart muscle of the myocardium, and then you have thin and thick filaments that slide one or the other, and this is possible thanks to the formation of cross bridges. We want to reproduce this, say, microscopic behavior at the macroscopic level by ordinary differential equations. So S is then sliding the deformation, and this is an ordinary differential equation that depends in terms of the say ionic species that have been computed, like the calcium ion that have been computed for the previous model. So the previous model passes through this model, this information, and this S is then provided by to the mechanical model that operate at the macroscopic level, which is there to provide us the deformation of the whole myocardium, of the whole ventricle, say, or atria. By that, if we solve this problem, we can have then the deformation of the myocardium. You see the ventricle here at different time instants. We go from 1/10 of a second to 60/10 of a second. We see the way the heart is deforming, and here you see it in action. This is the complete electrophysiology with the mechanical model. It's called the electromechanics core model. And once you solve it, you can reproduce the actual behavior, for instance, of the left ventricle, as the one that you see here. On the right-hand side, you actually see the displacement. It's a big displacement. You go up to 1.5 centimeters. On the left-hand side, you see what this gamma F is indeed the active force that is generated every single level. So you see the microscopic model on the left, which feed the macroscopic model on the right. This is a ventricle that is working properly, that is contracting in a regular way. These are the two ventricles together. We can better appreciate here the very complex mechanism that take place, which is basically the result of three concerted actions. There is a shrinking in terms of length, there is a dilation in terms of diameter, say, and there is a torsion. And this is the best possible way nature has provided us to have a perfectly functioning mechanical pump. Now, unfortunately, we have problems, right? So we know that more than 30% of the natural deaths in Western countries are due to cardiac or, say, problems for the cardiovascular system. And this is one example where you may have a very severe say, malfunctioning. If you see this ventricle that you see on the left-hand side, you have different zones. This is a real ventricle from a real patient. You have different zones. You have an healthy zones, which is characterized by the red color. You have a scar zone, which is basically death. So these fibers are not relaxing any longer. And then you have a gray zone, which is somehow in between. And for this specific patient, you see the way his say, ventricle is behaving. And what we're comparing here down there is what you have been simulated numerically with what you have been observing by what is called the SIN-MRI. SIN-MRI is the four-dimensional MRI, magnetic resonance imaging technique, 4D because you have the 3D in space, and you have a dynamic MRI. So you see, this is the curve of the volume of the ventricle during a heartbeat, and you see there is very good agreement between what we have predicted numerically or mathematically and what have been observed by SIN-MRI. And what you can appreciate here on the right is this, say, closed curve. This is the so-called pressure volume loop. it describes the way the pressure depends on the volume on, say, a regular ventricle, while what you see here is what you get for this specific ventricle. You can appreciate that the volume, say the surface of this closed curve of this area is much smaller. In particular, when you take the diameter, I mean the distance between the two vertical curve, this is called the stroke volume, and it tells you the amount of blood that is ejected by this ventricle. You see that this stroke volume is much smaller than the one that you would have on a regular heart, is perhaps less than the 50%, and this might create a problem indeed. I guess most of you have seen what happened last June 10th on the pitch at the Telia Parken in Copenaghen, where Chris Eriksen suffered of a very important disease, and actually he had an arrest of his heart. And this is very likely due to an arrhythmia problem. Arrhythmia indeed leads to the desynchronization of the flow rate through the mitral valve and the aortic valve, which are those that regulate the flux of blood to the left ventricle. And this will determine an inadequate, insufficient pumping action of the heart, which will, in very severe cases, lead to heart failure. And you see here indeed what's happening. The red refers to the aortic valve, the blue to the mitral valve. These are the spikes that regulate, say, over the time. These are seconds. You go from 0 up to 10. So these are 10 heartbeats. Those are the flow rate, which is measured in milliliter per second. And while you see here for the previous ventricle, the actual flow rate. So you can appreciate immediately that the value of these peaks or these spikes are much, much smaller. And this is because this heart is really unable to provide the right amount of blood to the rest of the circulation. So we try to help doctors to understand this. We try to help doctors to find, through numerical simulations, to find a priori answers to possible misbehavior of ventricles of heart, of people suffering from very severe arrhythmia, say. So far, we described the electromechanical part, and now is the turn of the fluid dynamics. We have blood in the cavities, in particular in the left heart. You see here the left atrium, the left ventricle, and the ascending aorta. You see the two valves. This is the mitral valve, and this is the aortic valve. You use the Navier-Stokes equations for the blood flow, and you account for the presence of, well, for those who are unaware of Navier-Stokes equations, those are equations that translate to basic physical principle, the conservation of mass and the conservation of momentum. And they provide us with two basic variables, u, which is the velocity field at every single point, at every time, and p, which is the pressure. Now we have an extra term here, which is there to regulate the behavior of the valves. So we model the valve as being objects that create an inertia on the fluid, and we add here a delta Dirac function that is concentrated on the surface of the valves, which multiplies the u minus u gamma k. U is the velocity field of blood, and u gamma k is the velocity of deformation, or the rate of deformation of the valves. And those are coefficients. Rk is the resistance coefficient, depends on the specific valve, and epsilon k is the thickness, actually R for the thickness of the valve. So when we solve this problem, we can then have an idea of the fluid dynamics that takes place in our heart. What you see here is the left ventricle. I'm sorry, the left atrium, which is on the upper part of the left heart. Say. It receives blood from this 4 vessels. You see the section 1, 2, 3, and 4 here from the lungs. This is oxygenated blood. This is the velocity, the modulus of the velocity. We go from 0 up to 70 centimeters per second, so it's quite sustained, say. And those are the vortices or the coherent structures that are created due to this, say, pulse effect. This is a well-functioning heart. We want to simulate what's going on there by solving the previous equations, and we end up by noticing that there is not actually a turbulent flow, there's a permanent transition toward a turbulent flow, but in regular heart, at least, the flow is still in a kind of quasi-laminar regime. You go actually from laminar to turbulent in a transient manner, but you never reach a fully developed turbulence because there's not enough time and not enough space for that. Then when the mitral valve opens, the blood enters into the lower cavity, which is the left ventricle, and through this left ventricle reaches the ascending aorta thanks to the opening of this aortic valve. You see again here, well, on the right-hand side, you see the velocity field. You have the opening and closing on the valve. You see the very fast dynamics and also the shrinking and the relaxation of the ventricle. And here you see again the coherent structures that are created. When the mitral valve opens, then you have a high-speed jet that come from the left atria and fill the left ventricle. This produces the formation of what is called the O-ring-shaped vortex, which is a coherent structure that rolling through the leaflets of the mitral valve. Then this big vortex breaks into much smaller vortices, much smaller coherent structures, and fill the left ventricle and move toward the apex. The apex is the lowest part of the ventricle. Then when the systole begins, systole means that the heart is contracting, then the aortic valve opens and the structures are flushing into the ascending aorta. Now, we use it for better understanding of what's happening in our heart. And as you can guess, there is no atlas, there is no images, the clinical images that can provide you this type of accurate and quantitative results. And then we used to help doctors in surgery, for instance, like in this case. This is a case of systolic anterior motion. This is due to the fact that the septum, that is the solid part that separates the left heart from the right heart, is becoming thicker than normal, maybe because of high pressure, say, over the years, and this inhibits the leaflet of the aortic valve to open completely. So there is an insufficient feeding of the aorta. So you have to operate and reduce the septum. But what is the design principle? Well, we try to help doctors to design the surgical intervention through the analysis a priori of the pressure jump through the valve. And this is a very good indicator of the healthiness of the heart flow. Now, this is the very last core model. In the end, we have to perfuse the myocardium to ensure that the myocardium, which is the muscular tissue, is fed by blood, because otherwise it will not be able to function, right? Now, this is not trivial in mathematical terms because we have to model the coronaries. And the coronaries are sitting on the external part of the myocardium, and these are called the epicardial vessels. We have tens of those, and these are those that you can actually see from medical images. You go down until 1 millimeter of diameter, say. But below this size, you still have thousands of little coronaries which are embedded into the myocardium that you cannot see with medical images. And so we try to reproduce them. So those, we produce them by elaborating the medical images. But those here, the intramural vessels, we have to guess. And we use mathematical models to derive them, say. Then we want to simulate the fluid dynamics. So for the epicardial vessels, we use three-dimensional Navier-Stokes equations. But for the intramural vessels, we have tens of thousands. We actually go up to 80,000 in this specific simulation. Well, we assimilate them to a porous media flow. But the porous media, well, this would be too simplistic, right? So we use three different levels, three different granularities of porous media modeling. And when you try to create a model that put together all these different models and let them interacting. And this is what we get. We have the Navier-Stokes equations for the epicardial vessels. We have the porous media Darcy flows for the intramural vessels. And we have three different classes depending upon the size of the vessels. But the important thing to note here is that all these classes coexist in a single environment. So we are using a kind of homogenization procedure, which yields basically that in every single point, we have the coexistence of vessels of different sizes. And then we have to put all this together and creating the right interface coupling conditions. So this is the system that we use for the perfusion. And how do you use it? Well, this is just one example, again, where we try to reach the clinical needs. Some of you probably know that if you are suffering from some heart dysfunction and you go to, say, hospital, the very first, or one of the very first tests is putting you on a cyclet, right? And then you can make an effort and you have a monitoring of the behavior of your heart during the effort, say. Now, in a more sophisticated environment, you are not only, I mean, doctors are not only measuring the pressure or say through the electrodes, through the leads, the voltage, but also the stresses with an echocardium that is operated there. And typically these are accompanied by the administration of a contrast liquid, which is a toxic substance, say. Now, we try to reproduce all this procedure mathematically, in mathematical models, with a good mathematical model of the perfusion of the myocardium. And then for real patients, you go here from patient number 1, P1, to P9, we have 9 different patients. We try to compare what you would get in terms of perfusion, comparing the map that is reconstructed from the doctors with the map that is reconstructed from the mathematical model, and compare them, right? And when you compare them and you go to, say, first of all, you can appreciate that those patients have very different type of vessels of coronaries. Those are the epicardial vessels. And this is not surprising because we are all different from one another, right? So at the end, our error when you compare all these maps in the maximum norm is below 1% of the 9 patients. So that's a good result if you account for all the uncertainty that you have in those cases. And again, the hope here is that tomorrow, in a few years, we will be able to provide this tool to allow doctors to make kind of virtual tests on patients, only on the basis of the shape of the heart of the patient, but without letting them undergo this very severe test. So that would be, say, from the social point of view, very important, and also from the economical point of view. And of course, it will not be invasive and will not, say, inject toxic substances to the patients. Let me summarize, trying to give you an idea of what we have been doing until now. We have different core models, and now we need to integrate all of them. And we need to integrate all of them for every single chamber. So you see here on the background different colors. You see the light red color on the right part, which is the left heart indeed, the left ventricle and the left atrium. Why red? Because this is the part that is interested by the oxygenated blood. And then you have the blue part, the one that is, say, has to see with the venous blood, which is the right atrium and the right ventricle. And in every ventricle, we have all these core models that we have seen before. And now we have to connect all of them together and all of them through these different chambers. And also to connect them to the torso, because then when you go to a hospital, they will take you the electrocardiogram. So we have to connect the model in the heart with the model on the torso, because you want to reconstruct mathematically the ECG, the electrocardiogram on your torso. And you also you have to connect it with the metabolism, because we have a very strong metabolic response for our system, and with the respiration. So we are not yet there with the respiration and the metabolism, but this will be, say, the landing point of all our model. Try to have a kind of holistic model that is able to describe as never before what's happening in the heart of different individuals, and hopefully to help doctors to face specific problems. And of course, you have to connect it with external circulation. And the external circulation is made of tens of thousands of small arteries and billions of capillaries, so you cannot use three-dimensional models for that. This would be out of reach. We use the analogy of electrical circuits, so a system of ordinary differential equations that we have to couple with a system of partial differential equations there. And this is just one example of application. So this is the left heart, which is connected now with the rest of the circulation. And you see the way it interacts actually through the vessels that are truncated, virtually truncated, but indeed connect with the external circulation without any spurious effect. All right. So I've only been talking about the mathematical part. So the equations and their impact at the clinical level. But in fact, we have to solve those problems. So you start from images. And the images can be CT scan, seen MRI, or MRI with, say, injection of gadolinium in order to better see what's happening. Use CT scan when you want to reconstruct, for instance, the coronary bed. Use the seen MRI want to have an idea of the shape of the ventricle and the motion of the ventricle. Use the LG MRI if you want to see the way you have scars on fibrous matter on the myocardium. And then you have to reconstruct the shape, and this is based on geometrical preprocessing. And once you have the shape, you have to introduce a grid, because in the end, you will solve the problem by going from an infinite dimension, projecting the whole system upon a finite dimensional subspace or a set of finite dimensional subspaces, which are represented by the values of the unknowns at nodal points. So in this specific case, we are using kind of 60 million hexahedra to reproduce the heart. And at the end of the simulation, we have the values on every single hexahedra. So the higher the number of hexahedra, the more accurate will be the solution. But of course, it will be more computationally expensive. Now, from the numerical viewpoint, you have plenty of problems. You have multiple scales in space and time. You have lack of data. Typically, mathematicians start with PDEs and they say, let omega be a computation, be a domain in R3, say, and consider this initial condition and these boundary conditions and this partial differential operator. Indeed, very often you lack boundary condition and initial condition for real patients. So you have somehow to guess them or to reconstruct them in a non-invasive way and by data simulation, for instance. You need to use splitting algorithms. You want to solve the global problem by proceeding with the different core models in an independent way, with the scalable preconditions, because you want parallel algorithms. When you use supercomputers, just to give you an idea, it takes about, say, order of a couple of days on a big supercomputer to simulate a single heartbeat, which means 1 second of real time. You need to reduce your model to project it onto subspaces of very small dimensions. And of course, you have to account for variability and uncertainty. And let me use these last 10 minutes or so to address one point, which is very, I would say, an argument which is very hot in these very days. And this has to see with artificial intelligence and machine learning and artificial neural networks. So far, what I've been presenting have all been based on basic physical principles. We start from the laws of physics, of physiology, in this case, the Maxwell equations, the Navier-Stokes equations, the Navier equations for the mechanical deformation, and so on and so forth, the Darcy equations, and so on and so forth. And then we have translated all those equations into mathematical equations and then solved them numerically. Now, you know that today there is a lot of discussion on the possibility to solve all this. I mean, not this specific problem, but solve PDE or solve a mathematical problem without laws, without equations, just from data. So this is made possible by artificial neural networks, which are an enabling tool for machine learning, which is the attitude of computers to learn spontaneously, which is part of the global, say, family of artificial intelligence algorithms, say. So for those of you who are completely unaware of that, what is an artificial neural network? It's a system that tries to reproduce the behavior of neurons in our brain. You have an input, the yellow part here, and you have an output. And in between, you have, barriers or layers of neurons that are cooperating, that are elaborating information and cooperating one another. And every single sphere here is somehow try to reproduce the behavior of a real neuron. You get input, you have linear combination of this input, and then you compose it with, say, a sigmoid function, which is a linear function, and you create the output. And through this output, you dialogue with the next branch of a neuron, say. You have input layer, hidden layers, and output layers. So mathematically speaking, artificial neural network is a function, phi, which goes from Rn, 3 in this case, to Rm, n equal 2 in this case, right? And this is the composition of different, say, functions, which are affine functions and nonlinear functions, say, which are called the activation functions. And those are exampled, the hyperbolic tangent, or what is called the ReLU, the maximum between 0 and x, say. Now, mathematically speaking, what is important to remark is that you have density results. You can theoretically prove that a neural network is capable of approximating any given function, and you also start getting error bounds, say, which depends on the number of layers and the number of neurons that you put on the different layers. And this is proven for, say, in the space of C0, for C0 spaces, C0 functions, or Sobel spaces. And here are some of the names that are associated with, say, this basic and fundamental result. And let me also mention that one of those results is due to Gita Kutiniok, who will be one of the plenary speakers of this ATCM conference. So these are the neural networks. All right. Now, you can very dogmatically think that you have either the possibility of solving a PDE by using the first physical principles, as I've done until a few minutes ago, or going to the lower part of this picture and just using artificial neural network, where you need to train your neural network by, for instance, in a supervised manner. You have training data, input and output, and then you have fresh new data, and you want to provide your output. So in principle, you could use these two layers in a separate manner, right? You can continue using, say, physics-based models, or on the other side, use data-driven models by disregarding completely the background. In fact, you can try to get these two different worlds to cooperate. These are the physics-based, where you have a kind of mechanistic understanding, and you obey the principle of causality. And this is the machine learning, or say neural networks, where you establish correlations, and you have to digest very big amounts of data, say big data. So here are some different keywords: multi-physics problem here, multi-scale problem, and the goal is to create a digital twinning. And here is the multimodality and the multi-fidelity, and you want to create a data-driven model. So in principle, you can regard those as completely independent. In fact, you can already use them in a cooperative manner. You can use physics-based models to regularize machine learning algorithms to avoid overfitting, or for augmenting the data where you have a paucity of data. You generate synthetic data by solving the PDEs with the left-hand model. On the other side, you can use, say, artificial neural network to create, for model reduction, to create models that are very, say, very small size and can be used to speed up the computation when we use physics-based models. On to unveil constitutive laws. Sometimes you do not know constitutive laws. You don't know what happens at the microscopic level, and you can use machine learning to have an idea what's going on at the microscopic level, or for parameter estimation, sensitivity analysis, and uncertainty quantification. So you already have different type of ways those two different worlds are actually cooperating. And let me mention one of these ways, which has been which is revealed particularly effective, say. And this is, as you see, this is based on the concept of PINN. PINN stands for Physics-Informed Neural Networks. And this was coined by George Karniadakis and these collaborators at Brown, and then, of course, has been generalized in many different ways. So the idea is that artificial neural network, will be used as a background scheme. However, when you have to create the loss function, the one that you have to optimize in order to select the coefficient, the parameters of the artificial neural networks, we can take into consideration the specific physics that is behind this specific problem that you are addressing. So basically, you are empowering artificial neural network with physics laws, say. And this is just a cartoon, right? And at the end, you will have a new solvers, which are new artificial neural network solvers for physics-based models. And let me try to show it on a very simple problem. The simplest problem you can dream of when you work in partial differential equations, the Laplacian. So man is Laplacian of u plus sigma u equal to f in omega, u equal to 0 on the boundary of omega. We know that you can devise a weak formulation in the Sobel space h10 of omega. We look for u in this space such that a of uv is equal to f of v, where a of uv is the Dirichlet form, namely the integral of gradient of u times gradient of v plus sigma u times v, and f of v is the right-hand side, is the functional, is the integral of f times v, say. This is the PDE. When you solve it in the classical way using Galerkin finite element method, for instance, what you do basically is to project this PDE onto the subspace of functions that are of this type, that are generated by piecewise polynomial linear functions that are continuous. And this is the classical form of the Galerkin finite element solution when you're using this type of function, right? And eventually you will end up with an algebraic system, which is not surprising because you start from a linear PDE, and in the end you'll have to solve a linear algebraic system. Sorry. So this is the finite element method that you see here. Let's try to see the way the finite element method compared with an artificial neural network to provide the solution of a PDE. The finite element method expresses the solution in terms of x, which are the coordinates, and u, which are the nodal values. And the space is indeed the space of functions that to any x associate a function that is parameterized through its nodal values at the nodal point. Now the ARN has a similar structure, unless that now u of x is the result of this combination of affine and nonlinear sigmoid functions. But still you can regard the solution as being dependent on independent variables and parameters that are weights and biases, which are those that characterize the artificial neural network, the neurons, right? So the structure is pretty much the same. You just change the role of parameters here and there. But there is a major difference. Finite element is a linear input-output map, whereas ANN is not, okay? So you cannot use the same Galerkin method for artificial neural network. You can replace it by collocation method, and then expressing the solution only at selected points. And you do that by updating or by tuning your loss function, taking into consideration the PDE and the boundary conditions in terms of residual. And by that, you can produce a solver which is purely based on artificial neural networks, right? You are exploiting the information, the knowledge of the physics, but embedded into the artificial neural network structure. Now, I'll skip the details. I'll just tell you that this is the algorithm, and this algorithm is here used, for instance, to solve inverse problems for PDEs. That's a very difficult PDE-constrained kind of problem when you consider it in a classical way in PDEs, and that's very demanding in terms of numerical solution. Well, here we are feeding the artificial neural network. We use a multi-fidelity artificial neural network. We use first a coarse network followed by a correction, high fidelity network and we create an output, we test our loss functional with respect to the observation. We consider automatic differentiation, we use a stochastic gradient descent, and you update the setting of our parameters. So this is very efficient, and it's really accurate. You can see here the way in the electrophysiology problem, the electrical field is propagated. You have here the high fidelity training data, the one which is based on the finite element high fidelity method, and down there what you get with the artificial neural network, and which are in the order of, say, 2% of error, which in practical terms is very well acceptable, say. And say we have to avoid the costly PDE solver, the forward evaluation at every single iteration, in the classical approach. You have low computational cost per iteration. You need about 1,000, say, training iteration with the artificial neural network, and you have almost, say, real-time solution of the problem with an error which is acceptable. And what we're trying to do here is to reconstruct the electrocardiogram on the torso of the patient, as well as the conducibility coefficient that takes place in the myocardium, which is very difficult to assess at the clinical level. You are solving a high fidelity inverse problem for PDEs in, say, in a way which is more efficient than using the traditional approach based on constraint optimization problem. This is just one example, and I'd like to conclude by acknowledging the contribution and the help of colleagues and students, both at the EPFL in Lausanne and the Politecnico Milano, and of course several clinicians and physicians that are really there to tell us which are the relevant questions for them and to guiding us toward assessing the quality and the relevance of our numerical results. And with that, I thank you, and I stop here. Thank you very much.